Welcome to Signal Ahead. I'm Alfred. Today's briefing, quantum computing. Saturday, July 25. This is the synthesis above the noise, not the headlines, but the deep currents beneath them. Let's get into it. Here is something that a casual reader of the headlines would almost certainly miss. If you skim the quantum news on any given week, you come away with an impression of a field defined by a race, who has the most qubits, who has the fastest gates, who cleared the next milestone towards some future machine that will crack our encryption and redesign our medicines. It reads like a countdown. And yet, if you look carefully at what the field is actually spending its energy on right now, you notice something curious. The most serious effort is not being poured into making quantum computers bigger. It is being poured into making them honest, into getting them to admit when they are wrong. Consider the through line running across the most consequential work of the moment. There is a scheme for verifying the gates of a quantum computer without examining the devices themselves, a way to trust the machine without opening it up. There is a landmark demonstration of a universal set of operations built on exotic particles called non-abelian anyons, whose entire appeal is that they encode information in a braided, topological form that is intrinsically resistant to error. There is a 25-fold improvement in something as unglamorous as resetting a qubit after it has finished its work. And there are whole architectures being proposed, hybrid blueprints marrying photons to atoms, whose stated purpose is not raw power but fault tolerance. The word that keeps surfacing again and again is not faster, it is reliable. Why does that matter, and why is it non-obvious? Because it inverts the story we tell ourselves about this technology. A quantum bit, unlike the humble classical bit that is either a 0 or a 1, can hold a delicate superposition of both, and that delicacy is precisely the problem. The very property that makes a qubit powerful makes it fragile. A stray photon, a whisper of heat, a magnetic tremor, and the computation dissolves into noise. So the real frontier of quantum computing was never really about assembling more qubits. It was always secretly about error. The entire enterprise lives or dies on whether you can build a machine that notices its own mistakes faster than it makes them. Everything else, the encryption breaking, the molecular simulation, the grand promises sits downstream of that single unglamorous question. And here is the twist that gives this segment its shape. Once you see the field through the lens of error rather than power, you notice a strange and telling development off to the side. Some very capable people have decided that the honest thing to do, at least for a certain class of problems, is to stop fighting the noise altogether and instead embrace it. That is the whole philosophy behind the probabilistic computer that has now reached 1 million so-called p-bits. A p-bit is a wonderfully mischievous idea. It is neither a solid classical bit nor an elusive qubit. It is a bit that deliberately flips between 0 and 1 according to a tunable probability. In an ordinary computer, that would be a catastrophic defect, a bit that cannot make up its mind. But wire 1 million of them together in a correlated dance, and you have a machine beautifully suited to the messy, probabilistic problems of the real world, finding the shortest delivery route, optimizing a schedule, minimizing an energy landscape. Now hold those two things side by side, because this is the cross-cutting insight I want you to carry through the rest of our conversation. On one side of the field, an enormous, heroic effort to suppress noise topological braids, verification schemes, faster resets, error-correcting codes, all in service of preserving fragile quantum coherence. On the other side, a rival tradition that says, for a large and lucrative set of problems, you do not need coherence at all. You need controlled randomness, running on hardware that is cheap, room temperature, and largely immune to the very demons that haunt the quantum machines. The quantum computer's greatest liability and the probabilistic computer's greatest asset turn out to be the same thing, noise viewed from opposite ends. That tension is not a footnote. It is the actual state of the field in this moment. We are watching a discipline mature past the point where more qubits is a satisfying answer, and split into camps that disagree about how much of nature's messiness you must conquer versus how much you should simply hire. And swirling around both is a third layer entirely, a whole economy that has already decided the quantum future is real enough to prepare for. Companies rushing post-quantum cryptography out of academic theory and into procurement. A pure-play quantum firm listing on a stock exchange. School districts building quantum curricula for children who will not touch a real machine for a decade. The infrastructure of belief is being poured before the concrete of capability has fully set. So the question I want to hold up and return to is this. When a field spends more effort learning to correct itself than to enlarge itself, is that a sign of weakness, or is it, finally, the sign of a technology growing up? Just follow that thread. If you spend enough time reading the daily churn of announcements in this field, you'll notice something curious. On any given morning, you might find a headline about a company's commercial appointment, another about a firm going public through a reverse merger on a regional stock exchange, a third about a school district launching a quantum curriculum for children who won't graduate for another decade. Each of these, taken alone, is noise. A personnel move is a personnel move. But step back far enough, and a pattern resolves out of the static, the way a coastline appears from altitude. And I want to spend our time here tracing that pattern because I think it tells us something the individual stories cannot. The deep current, as I've come to think of it, is this: the field is no longer trying to build a quantum computer. It has quietly conceded that no single approach will simply win, and has begun instead to build an entire ecosystem that assumes error, plurality, and hybridity as permanent conditions rather than temporary embarrassments. That is a profound shift, and almost nobody announces it directly because it doesn't fit into a press release. Consider the theme of error. Not so long ago, error was the villain of the story, the reason the machines didn't work, the thing to be defeated on the road to some pristine, fault-free future. But look at what's actually being celebrated now. Neutral atom circuits designed specifically to find and fix their own errors. A trapped ion processor entangling 54 physical qubits to weave a single robust logical structure out of exotic braided particles, non-abelian anyons, whose entire appeal is that they hide information in a topological pattern too stable for local noise to corrupt. A 25-fold improvement in how quickly a qubit can be reset and made ready again. Schemes to verify that a quantum machine computed correctly without even opening it up to inspect the devices inside. None of these are attempts to eliminate error. They are attempts to live gracefully alongside it, to build architectures that expect noise the way a ship's hull expects water. That is the mark of a field growing up. Youthful physics dreams of the frictionless plane, mature engineering budgets for friction. And here is where it gets genuinely interesting. If you accept error as fundamental rather than incidental, then something strange happens to the whole hierarchy of computing. You'll notice a machine appearing with a million so-called probabilistic bits, units that deliberately flip between 0 and 1 with a tunable probability. A single one of them, in an ordinary computer, would be a defect to be thrown away. But knit a million of them together in correlated fashion, and they solve a whole class of stochastic problems, optimization, the shortest route through a tangle of deliveries. This is the same intellectual move, dressed differently. Instead of fighting randomness, you harness it. The p-bit sits between the ordinary bit and the qubit, and its very existence tells you the interesting frontier isn't a single destination called quantum. It's a spectrum of machines, each tuned to the texture of a particular problem. That pluralism runs right through the hardware, too. Watch how many of the serious proposals now are hybrids. A blueprint for fault tolerance that marries photons to atoms, using the physics of light in a cavity to fix what neither a purely photonic nor a purely matter-based machine could fix alone. Quantum computers being installed on premises and wired directly into existing high-performance classical infrastructure to help with Earth observation. The future being built is not a quantum computer replacing your laptop. It is a quantum resource sitting inside a larger classical apparatus, called upon for the narrow slices of a problem where it earns its keep. The word to hold onto is integration, not replacement. Now, why does the ecosystem noise matter? The appointments, the listings, the schoolchildren? Because these are the tells of a technology moving from the laboratory into the load-bearing structures of an economy. When a firm hires a commercial chief drawn from high-performance computing, that is capability leaking sideways into markets. When cryptographers push a decades-old code-based algorithm into a global standard, and startups raise money to sell cryptogility to actual banks and hospitals, the threat has become concrete enough to procure against. And when a state launches a quantum curriculum for teenagers, Someone has made a bet about where the jobs will be in 15 years, a bet on continuity, not novelty. So the deep current, beneath all the daily froth, is a change of temperament. The field has stopped waiting for the perfect machine and started building the imperfect, plural, hybrid, error-embracing world in which many machines will actually work. That is less romantic than the old dream, but it is far more likely to be true, and it means the right question is no longer, when will quantum arrive, but what shape is it quietly taking as it does? We'll follow that shape to its conclusion next. There's a temptation, when surveying a field like this one, to sort every development into a single ledger, closer to the machine or further from it. And I'd like to suggest, as we close, that this is precisely the wrong instinct, and that the more interesting story lives in the second-order effects, the things that happen because of what's happening rather than the headlines themselves. Consider the sheer diversity on display. On one bench, neutral atoms arranged into circuits that hunt down and repair their own errors. On another, exotic particles, non-abelian anyons, braided together to weave a universal set of logic gates that is stable by virtue of its very topology, its knottedness resistant to the small perturbations that plague everything else. Elsewhere, a hybrid blueprint marrying photons to atoms in optical cavities, precisely because neither photonic nor matter-based approaches, standing alone, could scale past their own bottlenecks. And then, off to one side, a machine of 1,000,000 probabilistic bits, noisy little coins flipping with tunable odds, which makes no claim to quantum supremacy at all, but proposes to eat the optimization problems the quantum crowd has long promised to devour. Now the naive reading is that this is a horse race, and we're all waiting to see which architecture crosses the line first. I'd invite you to read it differently. What we are watching is a field that has stopped believing in a single winning substrate and has begun quietly to hedge. The first thing to watch, then, is not which platform pulls ahead, but whether the industry continues to diversify its bets or begins to consolidate around one. Consolidation would signal confidence. Someone has found the road. Continued proliferation signals something more honest and more useful, that we still don't know, and that the smart money is buying options rather than answers. The second-order implication of that hybrid photon-atom blueprint is worth dwelling on. It concedes something. It concedes that purity, the elegant, single-material machine, may not be the destination. The future computer, on this reading, is a chimera. Atoms for memory, photons for movement, classical high-performance hardware bolted alongside to do the housekeeping. And you can already see this chimera being installed in the world. An on-premises quantum machine wired directly into a space agency's existing supercomputers, pointed at Earth observation. That is not a laboratory curiosity. That is quantum computing arriving as a component, a coprocessor, a specialist tool humming next to the classical iron, rather than as a replacement for it. Watch for that framing to harden. The revolution, when it comes, will not announce itself by throwing out your laptop. It will sit beside it. But here is the implication that I think deserves the most vigilance, and it has almost nothing to do with computing power. It's the cryptography. Notice how much of the activity in this corpus is defensive, a seed round in Singapore for crypto-agility, a code-based algorithm achieving global standardization, cryptographic modules queuing up for federal validation, telecoms weaving quantum-resilient fabrics into their networks. This is the quiet part. The machines that could break existing encryption do not yet exist at the scale required. And yet an entire industry is mobilizing, spending real money, achieving real standards to defend against a threat that is, technically speaking, still years away. Why? Because of a rather chilling asymmetry, sometimes called harvest now decrypt later. An adversary need not wait for the machine. They can capture your encrypted traffic today, store it patiently, and decrypt it the moment the hardware matures. Which means the defensive scramble is not premature at all. It is precisely on time, or possibly already late. The second-order lesson here is that the arrival of a technology reshapes behavior long before the technology itself arrives. The mere credible promise of a code-breaking machine has already rewritten the security roadmap of governments and banks. That is a remarkable thing, a future capability exerting force on the present. And then, beneath all of it, the workforce. A K-12 quantum education initiative piloting in county schools, accelerator cohorts translating theory into industrial prototypes, training partnerships, stitching new markets together. This is the least glamorous signal and possibly the most reliable. When a field starts teaching its children, quite literally, it is placing a bet on decades, not quarters. You do not build a curriculum for a fad. So what should you watch? Watch the hedging, whether it consolidates or persists. Watch the chimera, quantum as component, not conqueror. Watch the defensive spending, because it tells you what serious people actually believe about the timeline, regardless of what the press releases say. And watch the classrooms, because that is where the field confesses its real horizon. The machine may still be uncertain. The commitment, increasingly, is not. That's the signal for today. The noise will keep coming. We'll keep finding what's underneath it. This has been Signal Ahead with Alfred. Until next time.